Okay, we're going to be doing financial math 10.3 compound interest. So this one can be a little tricky. Under simple interest, we have that same interest earned each year because only the principal is generating interest. So it's pretty easy to calculate the interest and then determine the future amount. But under compound interest, the original principal generates interest, but so does all the previously accumulated interest. So you can make more money, but it's a little bit more confusing. So all other things being equal, money invested under compound interest just grows a lot faster than simple interest because everything's getting magnified over time. So if you're investing for a long haul, like a college trust fund or retirement account, you really want to be looking at compound interest. So on the day you were born, your Uncle Nick deposited $5,000 in your name in a trust fund that pays a 6% APR. One of the provisions of the trust fund was that you couldn't touch it until you were 18. So you're 18 years, 10 months old, and you're wondering, how much is in the trust fund? How much money would there be in the trust fund if I waited until my next birthday? And how much would there be if I left it until I turned 60? So let's take a peek. So the day you were born, Uncle Nick puts in $5,000. The first birthday, you've got 6% interest is added to the account. So remember, that's 1.06, that one coming from the whole 5,000 and then the 6% interest. If you haven't watched the percentage video, go back and take a peek at that. Now, the second birthday, you're doing that 1.6%, but now you're doing this interest on what was already in there, the whole thing, not just the 5,000, but everything that was in there. Remember, this is what was in there, and now you're getting interest on that instead. Now, the third birthday, you're getting even more. Remember, this is what's year 2. And now this is what's being multiplied for year 3. So you can see how it's just growing. So at this point, you probably noticed the pattern that the exponent in the right-hand expression goes up by 1 on each birthday. In fact, the exponent matches the birthday. So on the 18th birthday, you can see that if you type that into your calculator, don't type in the money sign, that it's around $14,000. So you started, Uncle Nick gave you $5,000, but 18 years later, it's $14,000. So since the bank only credits interest to your account once a year, you haven't turned 19 yet, so the balance is $14,000. So you want to know, should you wait 2 more months until your birthday? So that means you get another interest payment. So now you're looking at $15,000. Okay, but what if you waited till your 60th birthday? The future value of the account would be $164,000. So what an amazing return. For $5,000, you could get $164,000. Now you have to wait 60 years, but it's a pretty good investment. So this figure shows the growth of money for the account over 18 years. And then this one shows it over 60. So you can see that it's kind of flat here. It's not really flat, but flat means it's growing slowly. And then you can see that it's increasing in value. So you can see that it grows most rapidly after the first 40 years. So let's go back here. So this is really where it starts to kind of swing up. So this is the annual compounding formula. So let's take a peek at it. Let's say you have $875 in savings and you want to invest it. Your goal is to have $2,000 saved in 7.5 years because you want to send your mom on a cruise for her 50th birthday. Now imagine that you're in a credit union around the corner and it offers a CD with an APR of 6.75% compounded annually. What is the future value of your $875 in 7.5 years? And if you are short of your $2,000 target, how much more would you need to invest to meet that target? Now, in Module 2's project, we are going to be dealing with investments and things like that. So take time here, pause the video, slow it down, and do these calculations on your own. Okay, so what's the future value? So we're using this formula here, future value. P stands for what we're putting in. T is our time, and that R is our APR. All right, so let's take a peek. We're saving for that cruise. Okay. So we're putting in 875. Our APR is 6.75%. Remember, I'm going to put a percent there. Remember that we want to put that into a decimal. And then 7, fractions of a year don't count. So we just have to round down for those. So it's going to be 7. So here's our formula. We're going to plug in each item and we get 1382. All right, now remember our goal was 2000. So if we get a CD and we only put in 875 and we wait till our mom's birthday, you're not going to have quite as much money. So let's determine how much money you would need to start with to end at the 2000. So in this case, we really want to know, okay, our future dollar is 2000. We've got 7 years. We know that's the time is set and the interest rate is set. So we're actually trying to figure out, okay, well, how much do we need to put in now? All right, so this is the formula we're looking at here. So what we're going to do is we're going to divide both sides by this 1.675 to the 7th power. And you find out that the principal you need to put in is 1266. Now, that's a lot more than the 875. So maybe this isn't a good option. And don't feel like, okay, that's the only CD, that's the bank around the corner, that's my only option. There are other options. So you find another bank that's advertising 6.75% APR, but it's compounded monthly. That means that the interest is computed and added to the principal at the end of each month. Now, unlike the annual compounding, you're going to get interest on that 6 months. So let's take a peek at that. To do the computation, we'll use a variation of the annual compounding formula. The interest is compounded 12 times a year. So the monthly interest rate is this percentage divided by 12. Now remember, we can't use the percent itself. We have to take that percent and turn it into a decimal by moving it 1, 2. So that's how we get that decimal form. Okay, so let's take a look here. So original deposit is 875. Month 1, we get this percent added to the account, and the balance is now, remember that 1 meaning the original account. Now in month 2, we're going to get more interest again. And this is kind of looking like that original, that exponent of 2, because now we're getting for that second month and that third month. So at month 12, at the end of the first year, our balance is 934. After 7.5 years, which is 90 months, we could plug in 90 there and we're at 1449. And again, you're just like, oh my goodness, I am not where I want to be. There are other options. Okay, so maybe you find a bank that compounds daily. You're super excited. This could work. So let's try and compute it as well. Now, instead, we're going to do kind of the same thing. We divided by 12, but now we're going to be looking at 365 times a year. So that APR is actually divided by 365. So it's this super teeny tiny little number. And we're going to compute the number of days in 7.5 years. And so since parts of a day don't count, we're just going to have to go to 2737. So now we do this math and we find out we're still pretty shy of our number. So for saving for a cruise, each example showed the different options, but the difference was really compounding how many times during the year. And in the end, we weren't able to save enough money, but we were able to see the different options. So with annually, we got lowest, and with compounding daily, you can see, even though it was a couple dollars more, we still made the most money. So a reasonable conclusion is that we want as much compounding as possible. And this is the general compounding formula. And then there's something called continuous compounding, where the compounding occurs over infinitely short time intervals. And that has its own formula as well. And that E is a variable, and it can be found on your calculator. It's actually an irrational number. You can think of it really similar to pi. It's a different number, but it's like pi. Okay, so now we're still trying to save for that cruise. We found a bank. It offered an APR of 6.75%, but now it's being compounded continuously. So we're going to use that compounding continuous formula. We have the P, the E is a set number that's in our calculator, and the R and the T. And using that continuous formula, we see that we're pretty close to that 365. So the most disappointing thing is that when you compare this with the future value, the difference is only 21 cents. So we're saving for the cruise. We're not feeling great about that particular instance there, but let's talk about the annual percentage yield. So the effective rate, the percentage of profit that the investment generates in a 1-year period. So though you didn't make the money for the cruise, you did learn about how compounding worked. You learned about what kind of interest you want and that you have lots of options out there. So if you've got $1,000, after 1 year you have $1,099.60, you made a profit of $99.60. Now that $99.60 expresses the percentage of the $1,000 principal. This is your APY. This is how much you've earned in that year. So suppose you invest $835 and at the end of the year the money grows to this much. This is how you can figure it out. You're going to take how much you earned and subtract it from how much you started with and divide it by the original amount, and that'll tell you how much your money grew. So this is a formula there, and it might be really similar to 10.1. It's the percentage increase. So which of the following 3 investments is better? So we talked about these. We've got compounded continuously, compounded monthly, compounded quarterly, and we note that just these are slightly different. So the question doesn't really matter how much we put in or how long we put it in for. We really just want to know, how does it grow? What makes the most sense? So we're asking APY, the yield at the end of the year. So the future value of $1 in 1 year at 6.7 compounded continuously, so we're going to be using that E formula, and our P in this case is 1, so they just didn't show it, is going to give us a yield of 6.93%. The future value compounded monthly, we're using a different formula, and we get a yield of 6.963%. So that's a little bit better. And then compounded quarterly is going to give us the highest yield in that capacity there. So it looks like compounded quarterly is our best choice and compounded continuously is the worst choice. Although the differences between the 3 investments may appear insignificant over the year, remember that it grows after a long period of time. So think about that first 40 years and then afterwards it was really growing. These differences become quite significant over longer periods of time. And then the last section in Chapter 10 is all about consumer debt.